Look up at the sun and you are looking at a future white dwarf. This is how ordinary stars end. When a star like ours exhausts its nuclear fuel, it does not explode. It sheds its outer layers gently into space and leaves behind its bare, dense core to cool forever. That core is a white dwarf, and it is the overwhelmingly common fate of stars. Some 97% of all the stars in the galaxy, our sun among them, will end this way, never massive enough to reach the violent collapse of a supernova. What they leave behind is one of the strangest objects in nature, a ball roughly the size of the Earth, yet carrying the mass of a whole star. Its average density is about 1,000,000 times that of water, so that a single teaspoon of its material would weigh several tons and, in the heaviest examples, the density at the center climbs toward 1,000,000,000 times that of water. To understand a white dwarf is to understand matter pushed to a quantum extreme, and a limit, discovered by a young man on an ocean voyage, that governs the death of stars. The road to this state runs through a star's old age. A sun-like star, having spent billions of years fusing hydrogen, swells into a red giant, ignites the helium in its core, and climbs to enormous size as an aging giant, developing a dense core of carbon and oxygen wrapped in burning shells. Then, in its final act, it blows off its bloated outer envelope in a slow wind, and the hot exposed core lights up that expanding gas from within, so that for a few tens of thousands of years it glows as a beautiful shell called a planetary nebula. When the gas disperses, only the naked core remains. A star that began with the mass of the sun leaves behind a remnant of only about half a solar mass, which is why, whatever their varied births, white dwarfs cluster tightly around 6/10 of the mass of the sun. What holds such an object up is the deepest part of the story, because a white dwarf has no fire left to burn. An ordinary star supports itself against gravity with the pressure of its hot gas, but a white dwarf has no fusion and is slowly going cold. It is saved by a purely quantum effect. The electrons inside it obey the Pauli exclusion principle, the rule that no two of them may ever occupy the same quantum state. As gravity crushes the matter, the electrons are forced closer and closer together, and because they cannot share states, they are driven into higher and higher states of motion. That enforced motion produces a pressure, called electron degeneracy pressure, and it is utterly unlike the pressure of a hot gas because it does not come from heat at all. It persists even at absolute zero. This is what keeps a white dwarf from collapsing, and it means that as the star cools it does not shrink, it simply fades. We can make this precise. The electrons fill up the lowest available states of motion first, stacking upward to a ceiling called the Fermi momentum, set purely by how densely they are packed. In a moderately compressed white dwarf, the electrons move slowly compared with light, and the degeneracy pressure rises with density in a particular way, as density to the 5/3 power. The energy of these packed electrons runs to hundreds of thousands of electron volts, vastly greater than the mere thousands of electron volts of ordinary thermal motion, even at 10 million degrees. The electron gas therefore behaves as though it were at absolute zero, so the structure of a white dwarf is a problem in quantum statistics rather than in the physics of a hot gas, and its pressure depends only on how dense the matter is and what it is made of, never on its temperature. But as we imagine piling on more mass and squeezing the star harder, something crucial changes. The electrons are forced to move so fast that they approach the speed of light, and the rules of relativity take over. When the electrons become relativistic, the degeneracy pressure grows more slowly with density, rising now only as density to the 4/3 power. That softening sounds like a technicality, but it is the hinge on which the whole fate of the star turns. A gas whose pressure rises only as the 4/3 power of density is, it happens, exactly on the knife edge of being unable to resist its own gravity. The switch to relativistic behavior sets in at a density of a few million times that of water, which is precisely the density reached in the core of a white dwarf near the mass of the sun. This is no exotic edge case then, but the ordinary condition of the heavier white dwarfs, and it is the physical root of a maximum mass beyond which no white dwarf can exist. The recognition of all this was a drama of 20th century physics. In the 1920s, the white dwarf was an embarrassment. Astronomers knew the faint companion of Sirius was fantastically dense, yet no classical physics could explain why it did not collapse once it cooled. The great Arthur Eddington sharpened the paradox. A white dwarf seemed obliged to cool, yet on cooling it would have no pressure to hold itself up. The resolution came in 1926, when Ralph Fowler applied the newly minted quantum statistics of fermions, and showed that the electrons form a degenerate gas whose pressure survives to absolute zero. The star is held up by quantum motion, not heat, and Eddington's paradox dissolved. But Fowler's picture had no upper limit, and it fell to others, notably Edmund Stoner, to add the relativistic correction that implied a ceiling on the mass. The definitive result belongs to Subramanian Chandrasekhar. In 1930, on the long voyage from India to Cambridge, the 19-year-old combined the relativistic quantum pressure with a realistic model of a star's structure, and found that a white dwarf made of carbon and oxygen could not exceed about 1.4 times the mass of the Sun. Stoner, using a cruder picture of a uniform sphere, had estimated a somewhat higher ceiling near 1.1 solar masses. Chandrasekhar's insight was to use the correct, centrally concentrated structure of a real star, which brought the figure down. Beyond that mass, the relativistic electrons simply cannot hold the star up, and it must collapse. When Chandrasekhar presented this, Eddington, the most eminent astrophysicist of the age, publicly ridiculed it, declaring that there ought to be a law of nature to prevent a star from behaving in so absurd a way. He was wrong, and Chandrasekhar was right, though the weight of Eddington's authority delayed the field's acceptance for years. Half a century later, in 1983, Chandrasekhar received the Nobel Prize, and the limit bears his name. The physics of that limit produces one of the most counterintuitive predictions in all of astronomy. Among white dwarfs, the heavier ones are smaller. This is the exact opposite of ordinary experience, and it is a direct fingerprint of degenerate matter. For a normal object, adding mass makes it bigger, but a white dwarf must generate more pressure to support more weight, and the only way a degenerate gas can do that is to compress to higher density, so a more massive white dwarf is a smaller one. Roughly, the radius falls as the mass rises, so that a white dwarf of one solar mass is about the size of the Earth, and a heavier one is smaller still. And as the mass creeps toward the Chandrasekhar limit, the radius does not merely shrink. It heads towards zero, the star trying to vanish into a point as the electrons lose their relativistic struggle against gravity. Refinements to the ideal limit, including the effects of general relativity and the capture of electrons by nuclei at extreme density, trim it slightly to somewhere between 1.37 and 1.4 solar masses. This strange relation is not just theory, it has been confirmed by a remarkable convergence of independent methods. The masses of white dwarfs in binary systems can be weighed from their orbits, their radii can be measured when they eclipse a companion. The light escaping their intense surface gravity is stretched to redder wavelengths by an amount that reveals the mass. The European Gaia spacecraft has measured the distances and brightnesses of hundreds of thousands of them, and the pulsations that ripple through some white dwarfs let astronomers sound their interiors like a struck bell. All these methods, gravitational, orbital, geometric, and seismic, agree with the degenerate mass-radius relation, making it one of the best-tested predictions in the physics of compact objects. Inside, a white dwarf is layered like an onion, though a very strange one. The bulk is the degenerate core, usually carbon and oxygen, the ash of the helium, burning that its progenitor never carried further. Around this lies a thin blanket of helium, and often an even thinner skin of hydrogen on top. Those outer layers are almost weightless compared with the core, but they matter enormously, because they act as an insulating blanket that controls how fast the star's stored heat can leak out. The degenerate core itself is an extraordinary conductor of heat, so it stays very nearly the same temperature throughout, and the steep temperature drop lies entirely in that thin outer envelope. It is the outermost skin that astronomers actually see, and it defines how white dwarfs are classified. Every type begins with the letter D for degenerate, followed by a letter marking the dominant lines in its spectrum. The most common, roughly 2/3 of all white dwarfs, are the hydrogen atmosphere stars. Others show helium or carbon or the lines of metals. Those metal-polluted white dwarfs are especially fascinating. Heavy elements should sink out of sight in such strong gravity within a few centuries, so their presence at the surface means the star is actively swallowing something right now, most likely the shredded debris of rocky planets and asteroids. A polluted white dwarf is, in effect, a probe of the composition of a dead planetary system, letting us weigh the rocks of other worlds. The closest and most famous example is Sirius B, the faint companion of the brightest star in our night sky, nicknamed the Pup. Its presence was deduced in 1844 by Friedrich Bessel from a wobble in the motion of Sirius itself, long before anyone saw it, and it was glimpsed telescopically in 1862. Lying just 8.5 light-years away, it is the nearest white dwarf known. It orbits Sirius in a long, slow dance, and that binary motion combined with modern space telescopes has made it the great testbed of white dwarf theory. Using the Hubble Space Telescope, astronomers measured how much the star's own gravity reddened its light, a shift equivalent to a velocity of about 80 kilometers per second, and from that read off its mass with precision. The numbers are staggering. Sirius B carries just over 1 solar mass, packed into a ball smaller than the Earth, with a surface temperature around 25,000 degrees. Its surface gravity is some 350,000 times that of our planet, so that a person who weighs a modest amount on Earth would, at that surface, weigh tens of millions of kilograms. Two pieces of fundamental physics meet in this single object. Its place on the mass-radius relation, a whole star crushed below the size of the Earth, is a direct confirmation of Chandrasekhar's theory of degenerate matter, and the reddening of its light is a test of Einstein's general relativity, the prediction that time itself runs slow and light is stretched deep in a gravitational well. In Sirius B, quantum statistics and warped spacetime are read from the same beam of starlight. Having no fuel, a white dwarf can do only one thing for the rest of time: cool. It is a fading ember, radiating away the heat stored in the ceaseless jostling of its ions, while its degenerate electrons, already effectively frozen, contribute almost nothing to that reservoir. The physicist Lev Mestel worked out the basic theory in 1952, and its key result is that the cooling slows dramatically with age, the luminosity fading roughly as time to the -7/5 power. A white dwarf lingers longer and longer at each fainter stage, so that the hottest young ones blaze above 100,000 degrees, while the most ancient have crept down to a few thousand over many billions of years. So slow is this fading that no white dwarf anywhere has yet had time to cool into a cold, dark cinder. The universe is simply not old enough, and the theoretical black dwarf remains, for now, a thing of the future. Because that fading is so regular and so well understood, white dwarfs serve as cosmic clocks. If you count them by brightness, their numbers drop off sharply at the faint end, marking the very oldest, coolest members of the population, the ones that have had just enough time to form and cool since their stars died. Reading the age of those faintest white dwarfs gives an independent measure of the age of the galactic disk, around 8 to 10 billion years, a valuable and completely separate check on the age of the cosmos derived by other means. The cooling, however, holds a beautiful surprise. As the core chills, the electrical repulsion between its ions eventually overwhelms their thermal jostling by a factor of about 175, and the interior undergoes a phase transition. The liquid core freezes from the inside out into a rigid, body-centered cubic crystal lattice. A white dwarf in its old age grows a solid, diamond-like heart. Crystallization releases latent heat, just as freezing water gives up warmth, and as the core solidifies, the heavier oxygen tends to settle inward and separate from the carbon, releasing yet more energy. Together these pump heat back into the star and delay its cooling by 1 billion years or more. This was predicted back in 1968, but it was only confirmed in 2019 when the Gaia spacecraft, having measured tens of thousands of white dwarfs, revealed an unmistakable pileup of them at just the brightness where crystallization should be slowing their fade. The theorists were vindicated by a traffic jam in the sky. Now return to the Chandrasekhar limit and ask what happens to a white dwarf that is pushed toward it. If a carbon-oxygen white dwarf has a companion star and steadily pulls matter from it, its mass climbs toward that fatal 1.4, and the density and temperature at its center rise until the carbon ignites. But here the degeneracy that once saved the star now dooms it. In a normal gas, ignition would cause expansion and cooling that regulate the burning, but a degenerate gas does not respond to a rise in temperature, so nothing holds the reaction back. The temperature soars, the burning accelerates, and in a runaway lasting only a couple of seconds a flame tears through the entire star and fuses it to heavier elements, releasing more energy than binds the star together. The white dwarf is blown completely apart, leaving nothing behind. This is a Type 1 supernova. These explosions are among the most useful beacons in the universe. Their light is powered by the radioactive decay of roughly half a solar mass of nickel-56, forged in the blast, which decays first into cobalt and then into iron over days and weeks, its gamma rays trapped and re-emitted as visible light. Because the exploding white dwarf is always near the same Chandrasekhar mass, It always makes nearly the same amount of nickel and reaches nearly the same peak brightness. That near uniformity, refined by a relation between brightness and how fast the light fades, turns Type 1a supernova into standard candles, cosmic mileposts of known wattage. It was precisely these explosions that, in 1998, revealed that the expansion of the universe is accelerating, and so pointed to the existence of dark energy. The death of a degenerate star became a ruler for measuring the fate of the cosmos. Exactly how these explosions are triggered remains a genuinely open question. In one picture, a single white dwarf feeds on an ordinary companion until it nears the limit. In another, two white dwarfs in a tight orbit spiral together and merge. In a third, increasingly favored in recent work, a white dwarf well below the limit accumulates a surface layer of helium that detonates, sending a shockwave inward to ignite the core, so the star never reaches the Chandrasekhar mass at all. The observed variety of these supernovae probably means that more than one of these channels operates in nature, and untangling them is a lively frontier of research today. A different white dwarf meets a different end. If the core is made not of carbon and oxygen, but of oxygen and neon, and it is pushed over the limit, the neon and magnesium nuclei begin to swallow the very electrons that hold the star up. Robbed of its support, the star collapses rather than explodes, crushing its matter until it forms a neutron star. And a neutron star is the next rung on a ladder of degenerate matter. It is supported by the same Pauli exclusion pressure, now acting on neutrons instead of electrons, and it too has a maximum mass, the analogue of the Chandrasekhar limit, known as the Tolman-Oppenheimer-Volkoff limit. The original calculation in 1939 gave only about 7/10 of a solar mass, but modern physics, tightened by the 2017 detection of two neutron stars merging in gravitational waves, places the true ceiling near 2 to 2 under fraction. Solar masses push past even that, and not even neutron degeneracy can win. The object collapses into a black hole. White dwarfs, neutron stars, and black holes form a sequence of ever more extreme equilibria, each governed by quantum pressure, and each with a sharp ceiling set by the onset of relativistic motion. At the frontiers, white dwarfs have become laboratories for matter at its limits. Surveys have turned up ultramassive white dwarfs sitting just under the Chandrasekhar mass, such as one recently found only about 130 light-years away, carrying more than 1/3 solar masses in a body no larger than the Moon, barely 2,000 kilometers across, spinning once every 7 minutes and wrapped in a magnetic field a billion times the Earth's, almost certainly the product of two white dwarfs that merged without quite exploding. Others pulsate, and by timing their oscillations, astronomers read their hidden interiors, testing the mass-radius relation and the crystallization theory from the inside, and even using the most stable of them as clocks precise enough to probe for undiscovered particles. The physics that Fowler, Stoner, and Chandrasekhar built a century ago, from the strange refusal of electrons to share a state, has grown into a precise, many-sided science, and at its explosive and magnetic edges it is contested and alive. Every white dwarf is a star that has died, and yet each one is still teaching us how the universe is built.